systems.
So once again, hello everyone. Thank you for coming, especially that's almost the last talk of the conference. Today I'm going to tell you about our journey to setting up and configuring connectivity across three clouds, Azure, GCP, and AWS. First, briefly about myself. I've been doing professional software development for over 20 years. Software development was my first love, but almost a year ago I joined the dark side. I became a platform engineer, and I must say that I do enjoy this work. In more details, what am I going to talk about today? So first of all, why do we need multi-cloud connectivity at all? I will show you a demo of cluster mesh, so our end goal, what we are aiming at. I will explain some connectivity options with cloud quirks and configuration knobs we experienced. Briefly explain Kubernetes and CNI, and along the lines of connectivity options and CNIs, I will show you some performance results. Why do we need multi-cloud connectivity? So to give you some context, I work for Form3, and in 2 words, Form3 is financial cloud. So basically, it provides a payment platform for financial institutions. It integrates across multiple payment schemas. This way, it makes integration easier and much, much faster for the customer, saving them time and money, obviously. We are a very technology-oriented company. We are fully based. At the moment, our production system is a single cloud AWS. There is a set of microservices written in Java and Go. Plus, we treat infrastructure as code almost as a religion, so we terraform everything. When it comes to payments and any financial system, you can imagine that we have quite high requirements. So as payment processor, we need to maintain very high SLAs when it comes to reliability and durability. Any outage in our business and we'll be out of the business. So we need to take and handle outages and errors without any data loss. Plus, obviously, considering the amount and volume of payments we process, we need to scale horizontally. So that's the background. And now let's move to top cloud outages last year. Let's take a look at a list. That's the list prepared by techgenix.com. And take a look at this one, and I have a question to you. How many of you have been hit by any of those last years? Raise your hand, please. Yeah, I would say that 30%, something like that. Yeah, myself, I was hit as well. So besides my regular job, I also teach at University of Warsaw. And I set up a Discord server to exchange messages and provide remote consultation for my students. And unfortunately, we noticed that it was down in November. So teaching is not like a critical domain. However, think about any finance, payments, or health systems. So instead of depending on one cloud, it's good to have like a backup and multi-active setup. So at Form3 at the moment, we are going multi-cloud. we are building new payment platform, which needs obviously be highly available, resilient, scalable, and performant. And on top of that, it needs to meet very high security standards. We've decided to go with three most popular cloud providers, AWS, GCP, and Azure. And we decided to use cloud agnostic technologies. So on top of those clouds, we will use Kubernetes, managed Kubernetes, NATS as messaging system, and CockroachDB as persistent storage. And what are we aiming at? I'm going to show you now a very cool Star Wars demo based on Isovalent Cilium demo. Cilium is Kubernetes CNI, and they provide CNI with cluster mesh capabilities. So basically load balancing across many clusters. And Isovalent is a company behind Cilium. So I've just adjusted a bit this demo to fit more clusters and some other naming. And now I'm going to show you what we would like to achieve, how we would like to avoid any disasters and survive any outage of any cluster or cloud. So I've prepared four clusters. The first one is in AWS. The second one is also in AWS. The third one is in GCP. The fourth one is also in GCP. Unfortunately, Azure was not very cooperative with me today, so only 4 clusters and 2 clouds. So this is a Star Wars-based demo. So we have X-Wing deployment, and we have Rebel-based service. So let's try to board our X-Wing and exec into our pod. Oops. It doesn't look well. Let's try to check if that's the correct cluster. OK, we are here, so I was missing a context here. OK, let's try to reach to Rebel base. That's a service, cluster IP service type. Oh, that's Rebel base. I'm sorry for this typo. Yeah, we got here. And we see that the response comes from GCP cluster 3. So basically, this is a global service, and it should be automatically load balance across my 4 clusters. So let's see if that's really the case. So let's loop 1,000 times. Let's call our service. And after each call, let's sleep 1 second, because otherwise the responses would be coming too quickly. And yep, they are coming, and we can track them. So we see that yes, indeed, those responses come from different clusters. AWS 1, GCP 3, GCP 4, AWS 2. So all 4 of them takes part in load balancing. What happens if we scale down one of them. So we are now at cluster 2 and scaling down AWS cluster 2. So now only 0 replicas, so it takes time, and now cluster 2 should be out of action. It seems so, but let's rule the Galaxy and let's switch to cluster 3 and let's disable cluster 3. That should be only 2 clusters, AWS 1 and GCP 4, and it looks like the case. And now let's switch to our last cluster. And now form 3 should rule the world. Or we have some hiccup. Let me run it once again. So unfortunately, that's not maybe the best. Okay, it is. So that may be like a network hiccup. I'm on Wi-Fi connection, so unfortunately that happens. Okay, at the moment form 3 rules the Galaxy, but we are not that greedy. Let's scale back one of the services. So now cluster 4 should come into the pool, and unfortunately it's not coming into the pool. I must say that this demo went so much better during my previous talk. So, but that's the Murphy law, right? When you are doing live demo and on your personal accounts with poor Wi-Fi, everything can happen. So it may also signal some problems with connectivity, and that's okay. We have one more clusters coming into action. So most likely my connectivity between AWS and GCP failed. So now most likely there are only 2 clusters in a mesh. So this is like my personal account. That's not our production setup. I'm using my personal accounts and HA VPN setup here. Actually, not HA VPN setup here. So that's only one more argument why we need better connection than VPN. So that would be our goal, to have automatically load balanced services that survive outage of any cluster. But to reach that level, first we need to ensure that we have resilient and high-performant multi-cloud connectivity. So that's what I'm gonna talk about today and explain what our way of reasoning was and what was the ultimate choice for us. Fast and Furious, that's my talk's title. Do you like Fast and Furious franchise? Who likes it? Yeah, obviously I'm a fan. Yes, so obviously fast. We are aiming at consistent rides. So, and we are aiming at one region. So we need to have low latency to achieve that. As I told you, we are planning to deploy payment systems, so we can't afford to lose any payment. So that's the fast part. What about furious part? A furious part is like sometimes we have insanely high requirements from our security team. And in the end, we need a safe landing, so this parachute landing might be a good picture and depiction of our use case. So what about our requirements? I've already mentioned that we aim at one region. Why one region? Because we can't achieve consistent rights with multiple regions. So we are aiming at one region at the moment with low latency, preferably under 5 milliseconds to guarantee those consistent rights for our messaging system and our persistent storage. We need to have steady bandwidth with multi-cloud deployments of NAS at CockroachDB. There's going to be a lot of replication. So we need to guarantee a certain level of bandwidth. Obviously, we need security and high level of privacy. Sometimes there are like legal requirements, for example, for confidentiality, that some data can't leave a country or a region. Obviously, high availability and fault tolerance in case of failure on any level, being it a link, device, or cloud point of presence. So what have we considered as our connectivity options? So the simplest way is to provide VPN. And that's what I used as a configuration for today's demo. That's basically encrypted tunnel over public internet. And the advantage is that all those free clouds provide HA VPN solutions. So it would be like ready out of the box. Another option is direct connectivity via cloud exchange provider. There is quite a big market of network as a service companies that provide network services in fully remote way. We can do a couple of clicks and have a connection with virtual router which connects AWS and GCP, for example. So basically, it's like they use direct connectivity options provided by cloud providers, being it Direct Connect for AWS, Interconnect for GCP, or Express Route for Azure. But this is like a hosted virtual connection or hosted virtual interface. So we don't buy the entire connection, we just buy a bandwidth. Plus, on top of that, they usually provide some sort of a virtual router because if we have many clouds, we need to route those connections among them. So that was one option, the second option. And the third one was direct connectivity via data center. So again, those two options are very similar. The difference is that instead of virtual provided as a service connections and router, we use physical router and connections directly bought from a cloud provider or some of the partners. What are pros and cons? With virtual private network, as you could notice, we go over public internet. So that's very unpredictable. So we can have spikes, like higher unpredictable spikes in latency. We don't have a predictable steady bandwidth. It's like, it depends. It depends on current traffic in the area. We have this unpredictable routing, which goes through public routes, so it can cross the borders. It may be more difficult to configure failover combined with other solutions, because the failover here is based on BGP protocol, and for example, some clouds have limitation in connecting different BGP sessions to a single router, or combining like VPN with direct connect on a single router. For example, GCP has this limitation. On the pros side, On the pro side is that it's relatively easy to set up. That's like with Terraform, it would take me like 2-3 hours plus provisioning. It may take like over 30 minutes on Azure. That's like the slowest cloud for me. But the big pro is that infrastructure as code is possible. So we can Terraform everything and no third-party dependency. So that's a big plus as well. In case of direct, but that was not the option. I can tell you that that was not the option we went for. So when it comes to other options, direct connectivity via cloud exchange provider. I told you that there is quite a big market there. However, we tested only Megaport. Megaport provides a big variety of connections and in many regions, so that was a good provider for us. Plus, a big plus was that they have Terraform provider, so we could Terraform all our connectivity. But what was the limit? For us, the problem was that at the time of testing, they didn't provide, still with one more note, still with this direct connectivity, either via cloud exchange provider or via custom DC, we still need redundant configuration. So we still need redundant links, we need redundant data center, redundant or high available router. We still have to have like a backup link in active-passive configuration. And for Megaport, the problem was that we were aiming at London region, and they didn't have 2 independent routes in London region. The HA setup in their case, it went through Frankfurt. So it was unacceptable high latency for us. It was definitely over 10 milliseconds, around 12 even. Too high for us. Plus, another thing is that we are in payment business. Usually we have contractual obligations and for some audit requirements. And all our vendors and providers must also meet a certain level of those requirements. And it was very hard to cooperate with Megaport. They didn't seem to be interested in getting this audit certification and clearance, so that was also a no for us. Eventually, we decided to use a custom data center. Obviously, maybe not our own custom center. We have a partner which operates data centers, and we have rented hardware there. So we went with this option when we have a very similar setup to cloud exchange providers, but instead of virtual connections, virtual interfaces, we have direct connections like interconnect or express route. Plus, we have physical router in our data centers, 2 data centers, HA router and resilient setup to automatically fail over to other links. The problem is that, unfortunately, our partner doesn't support infrastructure as code. So this data center configuration is like the manual work based on some change requests, etc. Plus, when it's manual work, which requires several levels of acceptance, it always takes time. So it took a couple of weeks to get everything up and running. There were long provisioning, configuration times, etc. However, on the good side is that we achieved very good predictable latency and bandwidth. Plus, we have flexibility to choose different cloud connections and different cloud exchange providers per region. So we can buy cloud connections from different partners. High-level connectivity design overview is very simple. Basically, we need to have everything redundant. So we have 2 DCs, HA set up for our routers, and redundant links to each of the clouds from each of the data center. The problem sometimes, the devil's in the details. The configuration for AWS, GCP, and Azure was turned out to be very different in each case. Even though it's all about networking, the resources provided by each of the cloud providers are very different, and they have different characteristics. So now I will tell you about those differences and some problems with some sort of a default configuration. So that's AWS side of our multi-cloud configuration. That's one way of implementing it. Here you see those edge routers in our data centers. We have 4 connections, or actually 2 redundant connections. So we end up with 4 virtual network interfaces, which are connected to Direct Connect gateway. So those are Direct Connect connections. Then we have a transit gateway in AWS that serves as a routing point. So on one hand, we can attach Direct Connect gateway to our transit gateway, and on the other hand, we can attach many VPCs. Several VPCs can share the same connection. In GCP, this configuration looks simpler, and it was simpler to implement. But still, we have 2 redundant connections. But the key part and the key difference is that we don't have anything like transit gateway. We need to prepare a transit network. So we have a cloud router which have interconnect attachments attached. This router resides in our transit network, and when we want to share this dynamic routes and make use of cloud router routing capabilities, we need to peer our virtual network to our transit network. So from virtual network, which is like VPC in AWS, we can't directly route to cloud router. Is it better now? Yes, it is. Okay, so, and this gonna cause some problems, but I will explain those later. With Azure, we have again a completely different setup. With Azure, the simplest way to share express routes is through express route gateway and virtual one. We have virtual one. Inside this virtual one, we have so kind of wide area network, and this is like meshing everything. So we have virtual hub. Once you connect to virtual hub, your VNets, there is like public visibility. Everyone can connect everyone. So that's kind of problematic from the security point of view. But that's like basic configuration, our default configuration, and it works. It works based on BGP protocol, Border Gateway Protocol. That's a protocol to exchange routes between networks in a dynamic way. So we don't need static routes anymore. We can rely on BGP and what prefixes, what side ranges are advertised from each cloud. So as we knew that we would share this one connection, but we still need like separate environments, separate VPCs which connect across clouds, we decided to use aggregate prefixes. We assign some big CIDR ranges to each cloud, and we wanted those clouds to advertise them to the other sites. However, there are some limits. First of all, there is a limit on advertised prefixes. That's different per cloud and per configuration. Azure has, and GCP, they support 200 prefixes being advertised. AWS only 100, but that's for transit virtual interface and one way. So AWS has more detailed and fine-grained control. So with aggregate prefixes, we are fine, because with those big CIDR ranges, our plan was that with big CIDR ranges, we won't hit those limits. Unfortunately, Azure does not support aggregation. So even though we can aggregate in GCP and AWS, we need to advertise each VPC separately on Azure side. And it caused another problem, because we had to reconfigure our data center routers, because our goal was to provide least privilege, to ensure we meet least privilege principle. So we decided on CIDR ranges and requested to configure the routers to do exact match of those advertised CIDR ranges. So nothing else being advertised won't pass. Unfortunately, due to Azure problem, we had to switch to or longer match, so we had to allow for those shorter prefixes to be advertised as well. Failover is organized again thanks to BGP with dynamic routing and configuring priorities, or for clouds discovering latency on a link with help of BGP med. We can decide, basically a cloud route, sort of a cloud router, can decide, because those are different wording and naming in each cloud. So this cloud routing device can decide which path should choose. It's good to configure, and now we need to think whether it's better to configure active-active or active-passive. And actually, in production environments, it's definitely better to configure active-passive. Why? Because with active-active setup, we can overutilize bandwidth. And we don't want it, because once we lose one link, we won't have enough bandwidth, basically. So for production environment, it's better to use active-passive configuration. And that was like our default configuration. And then InfoSec came into our site and told us to change everything. Maybe I'm over-exaggerating here. It wasn't that bad, but we need to take into account some security principles. So we want to have isolated environments. So for example, VPCA on AWS can connect only to VPCA on GCP and VPCA on Azure. We don't want those cross-connection across environments. So we need some sort of network segmentation. And it wouldn't be so bad. We can implement some sort of security groups or firewalls, and it would do. But from InfoSec point of view, it's not that simple, because there is that defense in depth principle. So one control mechanism is not enough. So we need to have at least two of them. So to implement least privileged network principle, we need to configure proper routing plus security controls in the means of security groups, firewalls, or rules. So what about our default configuration I described before? So the default configuration with default parameters for AWS Transit Gateway. Basically, AWS Transit Gateway by default propagates all associated attached VPCs. Plus, it automatically associates them to the default transit gateway route table. It's not that bad, because still we need to have static routes on VPC side, which means that we need to deliberately configure them. But when you require high security, it might not be enough. So the answer is to use separate transit gateway route table per VPC. This way, we could advertise custom prefixes to our VPC in AWS, and we can route only, and we can only have routes to corresponding VPCs in both other clouds. In GCP Transit Network and Router, the problem is even more complex. Because GCP doesn't support, if you remember, we peer our virtual network to our transit network. And GCP doesn't support any kind of filtering or custom advertising in that case. It's like all or nothing. So we can't have static routes also pointing to a peering connection or cloud router. So the only answer we found in GCP was to use HA VPN between GCP networks. This HA VPN between GCP to GCP network must be configured with BGP due to high availability requirements, because otherwise GCP doesn't guarantee high availability. it might be also possible to use router appliance in a virtual machine, but that's definitely too complex to configure and to achieve high availability setup. With Azure, some sort of VPN between Azure virtual networks might also be the solution here to guarantee this segmented routing. However, we still need to confirm that and do POC. So what about performance? So we did performance benchmarking with Hyper for throughput and to detect some performance issues to detect some connectivity issues, because with Hyper we have better detectability. We did also netperf test with TCP RR and TCP CRR tests. RR stands for request response, CRR connect request response. So the first one is when you keep your connection for a longer time and do requests over the single connection. The other one is that you create a new connection per request. And also ForGeo was used to do some comparison for HTTP 1.1 and basically 2.0 with gRPC. Also, there is that very cool setup for this performance tools in Kubernetes environment. That's like a set of manifest you can easily deploy, and you have like pods in a host network, pods in a pod network, and all the tools already configured, so it's easier to execute the tests. Here I have some comparison for VPN, because the first thing you need to decide is like your baseline performance. Baseline performance means node-to-node performance. So because with Kubernetes you have another layer of abstraction over your network, so it might introduce some extra overhead. And there is that saying that you can solve a lot of engineering problems by adding extra level of abstraction, but you can solve almost all performance problems by removing that extra level of abstraction. So here, fortunately, the difference between node-to-node and pod-to-pod connectivity is almost nothing. So they are almost the same. Here you see the results separately for AWS for each pair of clouds. And node and node, pod to pod, they look more or less the same. So there was no difference, not much difference at least, introduced by Kubernetes networking. That was done with cloud-specific CNIs, so they are pretty performant. When it comes to interesting thing here, comparing VPN and our direct connectivity via data center. So that's for each pair. We have on left we have VPN, on the right we have DC. So definitely DC is much faster, but actually not that much as I would expect. I thought it would be worse, so those results were kind of surprising for me. But that's good. That's good that VPN is actually, it seems usable in production systems, perhaps not very highly performant, but still usable. However, here you see this spike. So this is this anomaly when our GCP Azure VPN went crazy and P99 for this test went up to 100 milliseconds. So unfortunately, that's the drawback, and that's something I told you about with this unpredictable latencies or routing. For pod-to-pod connectivity, we see the difference between the pairs. So GCP Azure seems like the slowest. However, those differences are not that big. VPN is still slower, obviously, than direct connectivity. But take a look that P50 or P90 are not that bad. That's those spikes at P99, which make VPN unusable for our use case. There is, I told you that on top of this custom networking, we decided to use Kubernetes, and Kubernetes provides a completely different network model. So usually this is implemented by CNI plugins, and each CNI is a different specification provided by Cloud Native Computing Foundation, and basically Kubernetes implements CNI, and CNI plugins are required to implement Kubernetes network model, which provides pod-to-pod connectivity and provides IP per pod model. So basically each pod mirrors the behavior of a single virtual machine. It has its own IP, it can be connected to via this IP, and moreover, all pods, all containers inside a single pod behave like, can connect via localhost. So that's basically Kubernetes networking model. We also have this long list of CNI plugins. I've already mentioned that we, for our previous comparison, the performance results you saw, we used cloud-specific CNI. So each cloud must implement its own CNI because it implements its own networking. So we have AWS CNI, Google Azure CNIs, but besides that, we have like a bunch of third-party CNIs, like Calico, Cilium, Flannelweave, with sometimes more features that can be also used to replace cloud-specific CNI. Why would we want to replace this CNI? So be careful, because from my point of view, cloud-specific CNIs, they work pretty well. They are efficient, you don't need extra configuration steps, so that's easy to deploy. So if you don't need anything else, don't use those CNI, at least in the clouds. However, if you want to have some extra features like cluster meshing, which I showed you during the demo, or you want to have built-in encryption on network level, or you want to have some more advanced network policies, it might be useful to switch to one of these CNIs. And we did pretty extensive testing of Cilium. Cilium is a CNI plugin. It provides, the selling point is that they use eBPF. That's like dynamic insertion of eBPF code into Linux kernel to hook, for example, for some networking events. So that's much faster than IP tables. The problem with IP tables is that you have linear search with IP tables. So when you have a large number of ports and IP addresses configured in a single IP table, that's very slow. That's the selling point, plus high security and cluster meshing. How does the selling point stand in cloud? No difference. Why? Because in clouds you have limitations. You can't do so many things as Cilium can on bare metal machines. So, for example, they don't use eBPF host routing. They switch to legacy routing in clouds. So we don't see eBPF shining in clouds. And performance in terms of latency is very similar. However, we need also to observe CPU usage because Cilium might have a big impact and can increase CPU usage on a given node. So that's on a that's definitely a disadvantage. Does Cilium deliver on its promises with pod-to-pod routing, pod-to-pod connectivity? Yes, it does, but also custom cloud CNAs, they provide pod-to-pod connectivity at least across clouds, at least for those 3 clouds. Encryption. Cilium supports IPsec or WireGuard, and unfortunately our InfoSec offensive team detected that they don't encrypt traffic inside a single node. That's a no for us, so we can't rely on Cilium for MTLS and encryption. Network policies. Oh, those are very, very good for service-to-service communication because instead of configuring IPs in L3 or L4 layer, you can assign an identity for a namespace service or that kind of thing. And you can design your policies based on those identities. That's very useful. However, there is a problem with egress filtering in L7 layer. We tested that with L7 layer and egress filtering to public internet, it works like in 99% of time. It's not good enough for a payment system. So sometimes the packet, most of the time packets are, that's not only L7, but also based on fully qualified domain name. So around domain name resolution and filtering in real time, there is some problem. Service discovery and load balancing, it kind of works. However, you have problems with load balancing. Why? Because Cilium doesn't provide an advanced load balancing policies that's a simple random kind of round robin. If you think about production systems, it's not enough. You want to have like some sort of affinity, for example, toward local cluster. You don't want all your requests to be randomly transferred to another cloud. If one cloud in which you are, it's healthy, you want to stay in this cloud. Plus, think about canary deployments. You don't have any way to implement that. So, and that's only the top of the iceberg. There are some more Cilium configuration knobs and some more problems. However, they keep releasing new things and improving the tool. So maybe it will become production ready, at least for high requirements very soon. But unfortunately, our tools are not smarter than us, so it's on us to take proper decisions and to use our tools smartly, to know our tools, so experiment and test, and take your decisions after you have data. So data-driven decision, that's it. So thank you very much. I've run out of time a bit, but I'm open to your questions during a break. If you have any questions, I'm happy to share my experience with you. Thank you.